section is going to be looking at hypothesis testing. But in two new situations. We're going to do hypothesis testing. We're going to compare two population means. And the second thing is compare two population proportions. We've already done, hypothesis testing. Is the new stuff different from the old, right? That's the general question, right? Is the new mean bigger than the old established mean? Is the new mean less than the old established mean? Or is it just different, right? That's the left, right, and two-tailed test. And haven't we done very similar questions with proportions, right? Have the proportion of people who are vegetarians bigger today than it was in the past, less today than it was in the past, or just different, right? And we've looked at those kinds of questions. But those were essentially a sample and a fixed value that we consider to be true. So what we're going to be using today, I guess I'll do it over here. Let's do proportions because they're easier in many respects. Imagine that you have two groups of people. Now, those two groups could be all sorts of things. Couldn't one group be medication A and the other group was people medication B, and we looked at the percentage who lived, right? So cancer cures, right? How many, taking one treatment lived, how many taking the other treatment, right? So group A would be, one of them, group B would be the second. Groups could be women and men. Groups could be Scottish and American, right? Just two distinct populations. And we're interested in, is there statistical evidence to show that they are different in some way? Maybe the first group is bigger than the second. Maybe the first group has a smaller percentage than the second. Or maybe it's just different, but we don't know what that difference is. So I'll give you a story. So let's suppose that we look at Scottish people, and I'll call them group A, and we'll have American people, and we'll call them group B. And we went and asked them the same question. You have to ask them the same question, or it doesn't make sense. And you ask them questions like, what percentage of you last year went to a foreign country, right, on holiday? Right? So they got a sample of 200 Scottish people, and 150 of them had been last year on holiday, right, before the COVID. They'd been somewhere. And then they go and they get a different group of Americans, and for whatever reason, there's 300 of these, and they ask them, have you been to a foreign country on holiday? And 138 of them said they'd been on holiday to a foreign country. And this person, after doing this, was interested in, is there evidence that Scottish people, Scot people, go on holiday to foreign countries more often than Americans? So how do we set up a hypothesis test to test this? Well, I'm going to do a quick thing here. 75% of Scottish had said they'd been someplace on holiday, and only 46% of Americans. Right, superficially, would you agree that is very strong evidence that this is true, right? Scottish people go foreign countries, holidays more than Americans might. So we're going to have step one, set up the hypothesis. The null hypothesis is that the population proportions are the same. Now, you notice that these are samples, but can we imagine that behind these, there is a number? If you asked every single person in Scotland, there'd be a number, right? 82% had been in a foreign country, 12%. And the same thing's true about here. So in these stories, both groups are equally important, right? It's not one is the truth and you're trying to see if the other one could change the truth, right? They're both equally valid. And in this story, Scottish people are P1, right? So I'm calling them P1, right? And the Americans are P2. And I'm trying to find evidence that that is true. Right, that this number is bigger than that. Are we comfortable about the H not HA thing? In the homework, do you know they just give you a list of these with commas and you pick out of 5 choices and that would be the one you choose. So that would be the first piece of your homework. In this story, they'd be a significance level. And let's have that significance level at the 1% mark. Now I'm going to show you this question the long way, but only once. And then we'll show you the same question done on the calculator. So, to get this guy, step 2, the bit where you collect the statistics. The statistic that you're going to get is called Z score. And it's P1 hat, take away P2 hat, all divided by a guy called the standard error. Now, the standard error basically is the sampling distribution's standard deviation. And this guy has taken lots and lots of different versions, doesn't it depend on the question? Sometimes it's sigma over root n, right? Sometimes it's the square root of P naught, 1 minus P naught over n, right? In these stories, the standard error is distinctly ugly. The standard error is the square root of a guy called P hat, not P hat, P bar, 1 minus P bar, 1 over N1 plus 1 over N2. So you will just have that written down on a piece of paper so that it's there, right? I don't expect anybody to go around memorizing that ugly letter. And to which you're going to say, wait a minute, that you said P bar, do you not mean like P hat? No, I don't mean P hat. Because not only is that formula ugly, before you can even calculate that formula, you have to get P bar. And how do you get P bar? You add the two data sets together. So do you see how here this is 150 people said yes, and over here is 138? Do you see how this is 200 people and you see this is 300? If you want to see what the formula looks like, if we say response 1 plus response 2, in this case it ends up being 150 Scottish people and another 138 Americans over a grand total of 500. So do you see that this P bar ends up being 288 out of 500. This P bar is 288 divided by 500. And that comes out as 0.576. Have I already convinced you that this is a we're only doing it once question? Because we haven't even got to the answer yet. This is just a preamble, right? This is us still hunting for this guy. So if I planned it right, I would have given myself more room, but since I haven't, here goes. It's going to be the square root of 0.576 times 0.424 times 1 over 200 plus 1 over 300. God in himmel, that isn't even pretty. Square root. The p-bar, nothing 0.574, times 1 minus the p-bar. That's where the 0.424 came from. Multiplied, in brackets, 1 over the first sample size plus 1 over the second sample size.
I believe it was supposed to be 0.576 instead of 574.
I think I've written 6. Oh, I wrote 6.
Sorry, your calculator.
Yes. Now, did I do the other? Ah, good, I did that. Now, I guess that would be a good example of why partial credit is very useful. Can you imagine if I had just done this, I wouldn't have known, probably, and I would have screwed up. So it looks like the standard error comes out as 0.045. So the z-score is p1 hat, 0.75. Take away p2 hat, 0.46, divided by the standard error, 0.045. I'll do that now. So 0.75 take away 0.46 is that, divided by 0.045, and I am looking at a very interesting z-score. I like that kind of number. Can you tell that this is going to be statistically significant, even although I haven't finished the question? Can you tell? How do I know that this is going to end well and we're going to get some conclusions? What's nice about this Z value? It's nice and big. Don't big Z values tend to generate very small P values, and that's where significance is coming from. So step 3, let's find the P value. Well, it's a probability that you get a z-score bigger than 6.44. If you want to get a z-score bigger than 6.44, oh, whereabouts in the calculator is that head?
Distribution, normal, CDF.
Right. And since I'm looking for bigger than 6.44, I'll do 6.44, comma 999, comma 0, comma 1. And the answer I get is one of those ridiculous E guys, roughly that guy, which I'm not going to write down with zeros. Can you imagine how many zeros that would look like? Right, wouldn't it be 0.10 more zeros than a 6? Right, so stage 4 conclusion. I'm running short of room here. Is our p-value less than alpha? Do you see it's the same kind of process as yesterday? Very similar at least. Is this weird tiny number less than 0.001? And the answer is, of course, yes, it is. So conclusion. This is statistically, so what's the rest of my sentence going to be? This is statistically
significant.
Significant, yes.
So in the homework it said they either had we failed to reject
that sentence
null.
thing.
So that's but that would be the opposite if it were bigger.
That's not statistically significant that
right.
way.
But if
when
it is, it's
we reject it.
Okay. It was confusing getting used to that language.
It's very lawyer-esque, isn't it? It's full of rejecting this or failing to reject that kind of way of saying things. Right. But this means then essentially, isn't there evidence based on this analysis here that Scottish people do in fact go on holiday more often than than Americans? Now, this analysis could have been done when you were comparing two treatments. Can you imagine there's two new cancer treatments, and success would be the number of your patients who are alive after 5 years. And normally when they do medical things, you can't say the person's going to live forever, right? Everybody dies, you know. So you decide success based on percentage of my patients who are alive in 5 years. That would be a good measure of success. So you've got old cancer treatment, right, and new cancer treatment. Can you see you could do the same analysis? And what that would allow you to do is that would allow you to say things like, this new treatment is better than the old treatment. And so you should be using this. They've done that in the past. Do you know when they were doing cancer treatment, right, when it was at its beginnings, they had all sorts of treatments. They had chemotherapy would be a very big, right, radiation treatment essentially. But they also had various pharmaceutical things that you would take, right, drugs that you would take. And they were to combat the cancer. And what they discovered is that very often the best success rate isn't doing only chemo or only drug treatment. That the greatest success was actually done when you did a combination of both together. And how they came up with that was simply just by having a clinical trial where certain cancer patients were only given the chemotherapy treatment. And they looked at what percentage of them were alive in 5 years. And then the ones that were given the combined treatment and what percentage of them survived. And it was statistically significant that it was more successful, right, to do the chemo and drug therapy. And that once that gets pretty much accepted by the medical community, isn't that kind of what you get if you have cancer? Yep, you're going to get the cocktail of drugs. And that's another thing. Very often it wasn't one drug, it was a cocktail of drugs. The cocktail of various pharmaceuticals was better than just giving them one cancer treatment pill. And you know, the advantage of that is that even if you can knock off a couple of percent, isn't that pretty good for those 2 people out of 100 who are now alive? And so any increase that's statistically significant in that situation would be considered a big plus. Of course, if you're going to do that kind of treatment, would you agree you better use a 1% significance level, just in case you got, by chance, a little bit more success rate out of one, and it was just, you know, the luck of the draw. So that horrible question is now going to be done on the calculator. I really only need to keep track of the key data, right? So you've not seen this guy, but if you were a betting person, where do you think it's going to be heading? Where do you think this test is going to be?
Would it be 2 proportion T
Oh
test?
God, you're ahead of the game, isn't it, in stats over at test? And now it's going to be, is it the 2 proportion Z test she is asking? Yes, it is. Now, you notice you just got to get used to the way it's written, right? And that's fine. We can all get used to that. So X1N1 is going to be the Scottish. So in the Scottish, it was what, 150 of them out of 200. So that's where that data goes. If you look at the second group, the Americans, it's going to be what, 138 out of 300. Now, what were we trying to prove here? P1 not equal to P2, P1 bigger than P2, P1 less than P2, because we have to choose one of these 3, don't we? P1.
Is it greater than P2?
Yeah, it was. You see it here, right? And then we can do the calculate. And fingers crossed. Do you see that ugly e to the negative 11 guy? Remember our ugly e to the negative 11 guy? You see it's the same guy. Remember our Z score was what, 6.44? Can you see that one 6.44? 6.48. I'm not going to 6.43. I'm not going to argue about the second decimal place. Maybe I rounded off too much with my standard error. You remember when I did the standard error, I stopped here. Maybe they did the standard error to 6 places. That's not a biggie. Right, that's rounding off, right? It's the same story. Do you see how quick that was? How you got to the key? Isn't the key the p-value? Because once you get to the p-value, is that number less than 0? Sure is. Statistically significant result. So I'm now going to do another story, but purely calculator.
I have a quick question.
Yes.
Did we use 2-prop z-test before, or was that 2-prop z-interval?
Interval we used
Okay,
before.
I'm getting mixed up. Okay.
Yeah. We are doing tests, hypothesis tests. So think test and you'll pick the right menu. When you're doing confidence intervals, think interval and you'll choose the right menu. Right? Interval uses intervals, tests uses tests, because they do look very, very similar if you're not careful. Right. Actually, I think you put in almost the same information as well, don't you? But what you get out is a little bit different, right? So let's have a story that we've got. And so we're going to have English majors, and we're going to have science majors. And I believe that people who are English majors read books for fun more often than science majors, right? That's my gut feeling. So we're now going to test it. And so a social scientist, that's probably the kind of person who might be interested in that, decided to ask 100 English majors, and they went and asked them, in the last week, have you read a book just for entertainment purposes, right? Not for class, just for entertainment purposes. And 75 out of 100 said, yep, I read a book last week, or I was reading a book last week for entertainment. And they went and asked, let's say it's 300. And they went and asked them that same question. And 168 of them said, yeah, I'd read a book. It was a science fiction book, but I read a book. It was for entertainment. Let's find out what that looks like. Well, that one I don't need to do. Isn't that 75% of them? This one here is 168 divided by 300, and I get 56%. Would you agree that it definitely looks like what I thought was true? Isn't the evidence pointing in that direction that English majors tend to read books more often for entertainment than science majors? I need a significance level in this story, so I'm going to just stick to my 1% again. So let's look at what this question would look like. Well, you always start off with the null hypothesis that both groups are essentially the same, right? They both read books for fun equally often, right? So far, so good. Now, in this particular story, are we looking for evidence that P1 is greater than P2, less than P2, or just different from it, not equal to it?
Greater
Be just
than.
different.
No,
Well, yeah, it could be different. I think, or at least I hoped I had in my intro story, that the social scientists thought that English majors would read more often, right? So somewhere in the written sentence, there'd be something like that, right? Now, if the story said the social scientists believe that the two groups are different, then they wouldn't have chosen the not equal to. And maybe they say, I think the first group's less than the second, then you do a less than. This is a right tail test, isn't it? The other way is a left tail test. and a not equals to is a two-tailed test. Isn't that exactly what we did yesterday? Bigger than is right, less than is left, not equal to is two-tailed. Right, we got everything we need here. Let's see what it looks like. I'm going to go Start, Tests, Two Proportion Test, hit the enter. Group 1, that I'm calling N1 and P1, that group there, right? We have 75 people out of 100 English majors. And then we had 300, rewind that. We had 168 out of 300. And we're still doing the greater than. I'm going to go a side issue here. Do you know that there's a lot of pictures in these questions where they give you 4 pictures and say which one is it? Okay, I'm going to hit draw. Oh, unfortunately, this answer is so tiny you can't see the shading. But if it was a decent number, you'd see it. Right, so I'm just returning very quickly back to that guy. And I'm going to go and do calculate now. And the p-value, which is essentially all we need, the p-value here is 3.8 times 10 to the negative 4, which I think I can get away with writing like that, right? I don't always write it down if there's tons of zeros, but in this case, would you agree I could probably do it? It's not too onerous. So we are pretty much ready to go to conclusion, aren't we? Is our p-value less than our alpha? Is this fella less than that? And the answer is yes. So this is statistically significant. And can't we then say there's enough evidence to reject H naught and so HA is true? But in English, wouldn't that mean that, yeah, that it's statistically significant result? We've proved that English majors will typically read books, novels for entertainment more often than science majors.
I have a question.
Yes.
If the sample sizes of the two groups were the same, it wouldn't be necessary to go through this whole process, right? Because you could tell which proportion was greater than the other.
Well, you'd still have to, because let's imagine both groups were 100. Wouldn't this could be 75 and this could be 56, right? You could still do that, right? But couldn't you get 56 and 75 by just sheer chance? There's no, it doesn't guarantee it. You can't do the guarantee part unless you find the p-value. What's the chance of this happening? The fact that the samples are the same size really doesn't enter into the situation, right?
Okay.
It would be helpful to have decent numbers. That would make a big difference. I think 100 and 300 is getting there, right? I'd rather have 1,000 than 3,000, but that would cost too much. But it would do. Right. I'm going to see if I can get one that isn't negative 11 or something, right? Let's get one that's got a number that's kind of fighting the region. So we are going to have vegetarians against meat eaters, right? And since I'm making this up, I can insult anybody I like, unless somebody here is a vegetarian, in which case I won't. Anybody want to admit to being a vegetarian, because I'm about to insult you, and if you are, I'm not going to insult you then. Okay, that means that I'm allowed to insult vegetarians, because none of you here are going to feel picked on, right? So they collected 200 vegetarians, and they went and asked them, are you happy? And 50 out of the 200 said, yeah, I'm happy today. And they got 150 meat eaters, and they asked them, are you happy? And 41 of them said, yeah, I'm happy. And the social scientist was interested. Are these two groups different? Are meat eaters and vegetarians different about how happy they are? Now, we all know that vegetarians are miserable people, right? They're not happy. I got my insult in. 25% of them are happy. This guy over here, the meat eaters, it's basically not that much different. So maybe that's statistically significant, and maybe it's not, right? We're going to do the hypothesis test analysis. Now remember, the social scientist went and said he wanted to test if there was a difference, right? He had no preference on how the difference went, just wanted to see if they were different. So that's going to give me a null hypothesis is that they're the same. And if you say, are they different, doesn't that mean that they're not equal? So we're going to use a two-tailed test. Are we comfortable with that combination of that hypothesis test based on the story that I gave? What's your gut feeling? Do you think that's big enough to make a difference? Borderline, maybe, maybe not. Right? So I can imagine that this social scientist might have a job with a magazine or a blog online or something. And once they come up with this result, they are going to have a headline. So let's find out what the result is, and then I'll tell you what kind of headline they might have. So put it on here so you can see it. Stat, tests, to proportion. So 50 out of 200 vegetarians were happy. 41 out of 150. And we are doing the not equals. Do you see the not equals, Joyce? The first one. Are we comfortable with the data input? 50 out of 200, 41 out of 150, and not equals to hypothesis choice. And so when I hit calculate, I will get a p-value of 0.622. Is the p-value less than alpha? Would you say that's a definite no? So this is not statistically significant. And a magazine article might be new survey out. Vegetarians are just as happy as everyone else. Actually, that's not true. Doesn't this analysis just mean that we don't know if there's a difference? Remember, not statistically significant doesn't mean we've proved that they're equal. Not statistically significant means we have found no evidence that they're different. It doesn't mean that they aren't different or that they're not different. We just didn't find any evidence one way or the other. But a lot of articles and people who don't know statistics treat this as if you've proved that. And that's not actually what we've done. In a bad sort of a way, haven't we proved nothing? We don't really know. That's what we should be saying. We don't know if there are differences. If I wanted to work on this fella, because I still think that there was a difference, what would be the only thing I could do that might get me some statistically significant result? Right, I believed in my gut that vegetarians and meat eaters are different. Now, it might be, I might think vegetarians are happier than meat eaters. It's fine, right? But I've got in my gut feeling, I think they're different. Is there anything I could do, a new survey, right, that I could do that would help?
Would you just increase the sample size?
Yep, that's exactly what you would do. You know, when you increase sample size, don't you get more accurate information? And if you get more accurate information, if there is truly a difference between the two groups, it will eventually show up. If that difference is negligible, like, yeah, there's a difference, but it's like 0.1% difference, would you then enter the realm of, yeah, they're different, but it's not that important? If they're statistically significant, it doesn't always mean that you found something important, right? All it says is that you've proved that they're different. But see if that difference is minor, very, very minor, it's not that big a deal, right? So we'll look at that from that perspective. So are we happy with hypothesis testing comparing two populations?
I have another question.
Yes.
About the not equal sign.
Yes.
I'm a little confused. Let's say if I was checking it by hand, how would you calculate the p-value
It would
with the
depend.
not equals?
Oh, yeah.
Because
Well, yeah,
you can't do probability of z greater than or equal to.
Okay, let's see if I
number.
can find my guy. If I got him handy. Right. Imagine it was this fella here, right? Since I've got the hand working, right? Won't this here be a number, right? Now, it'll be a positive or a negative number, depends on how the data comes out. If it's a positive number, your p-value will be the probability that z is bigger than this positive number. If it's a negative answer you get here, your p-value will be the probability that z is less than that negative number. So that's how you'll get your p-value.
Okay.
Right. So you'll calculate z, right, using all this stuff, and you'll get 1.8. Well, your p-value will be the probability that z is bigger than 1.8. Let's say you do it and it's negative 2.1. Your p-value will be the probability you get a z-score less than negative 2.1.
Why isn't the probability of z-score greater than negative 2.1?
Well, negative 2.1 is implying that the first one's less than the second, so you should be doing a left tail.
Okay.
When you do a two-tail, the z-score decides on which end you're getting your percentage. When you do a two-tail, you're basically getting either this guy here or that guy there, right? If your z is positive, it's going to be this side, right? But if your z is negative, you're going to get it on that side.
Okay, I have to think about it, but that's starting to make sense.
Right. So when you get your p-value, if you're doing it by hand, and it's a two-tailed like this, see if this guy in here ends up being 0.02 for argument's sake, right? Your p-value is actually double that. Because the way the two-tailed test works is you're assuming that both ends are equally likely. The fact that you found one side, because that's what the data says, doesn't mean that you might do it at a different time and it's at the other end. And so you have to basically double these numbers. You don't need to when you do it in the calculator because it already does that for you. So a two-tailed is probably going to be the most awkward one to do by hand because of that. A left and a right is easier, it's cleaner, right? The p-value is the p-value, you don't do anything to it. Right, back to this. Are we comfortable with this proportion story? Right. Agree? So where we're moving off to now is comparing two means. Right. So I'm going to show you one of these by hand. Just to show you this is how you would do it if you wanted to do it by hand. And then we will do calculators. If I did them all by hand, we wouldn't get finished, right? They take about 10 minutes each, and they're quite laborious. But here's a story. So here we will have a story about male mountain lions and female mountain lions. Well, the zoologist was interested in looking at if there are any differences, right, between male mountain lions and female mountain lions. And we're talking about their weight, right? But it could be their height, that would be their shoulder height probably, or their length, front to back. In this case, we'll make it their weights. And he believes that male mountain lions are heavier than female mountain lions, right? Because in some breeds, the male is heavier than the female. In other species, isn't the female heavier than the male? That's a little bit less common, but it does happen. In quite a lot of species, aren't they pretty much about the same weight? I'm making this up because I don't know. I think tigers are probably, female and male tigers are probably about the same weight, right? And I'm thinking, if you talk about African lions, I think male African lions might be a bit heavier than female African lions, just off the top of my head, right? So you can imagine for various species, you might want to figure that out. So how do they, if they are going to write a textbook for zoologists, and one of the things they want to mention is weight, shouldn't they be able to say, typically a mountain lion that's a male will be heavier than a female? So let's see if that's backed up by the facts. So in this story, he collected, tranquilized, whatever, 200 mountain lions. Actually, he'd probably, if I was him, wouldn't you just go to a zoo? Because they've probably got the weights of all their lions and just do it that way, right? Less work. But anyway, he got the number, whatever weight it was. And the average weight, because I have no idea what a mountain lion weighs, is 130 pounds, just for argument's sake, right? And over here, he collected data on 250 female mountain lions, and the weight of those was 127. Not a lot of difference, at least in my story, agreed? But we still want to see, is there evidence that the male is heavier than the female? And we're going to take a significance level of 10%, because I'm not too worried if I get it wrong, right? Yeah, 10% of the time I will. Oh, and one extra piece of information. Have you noticed that when we talk about means, X bars, isn't there two versions? Sigma known, sigma unknown. Don't we do that with confidence intervals as well? Didn't we do that yesterday? In this case, sigma is known. So the population for this guy is 5. And for these, it's 3. So what does that tell me? Roughly that tells me that male mountain lions vary in weight a lot more than female mountain lions, right? So just a bigger variation in male weights, right? And females a little bit less variation. Right, we're going to put this package together. So step 1, our guy. Now, remember what we called the population mean. The sample mean's called X bar 1, but what would the population mean? What would we use? It's a Greek letter. Can you write the letter down even if you can't remember it? It was that guy.
Is it mu?
Yeah, it is. So the null hypothesis is that the population, you know, the average male and female are the same way. In my story here, aren't we trying to prove a right tail test? We've been asked to see if there's evidence anyway that males are heavier than females. And what other thing have I forgotten in my story? No, I haven't. I take it back. I was going to say I've forgotten the significance level, but I haven't. So we're cool. Now, what does the Z-score look like? Well, it's X1 bar, take away X2 bar over standard error. Does that look familiar? Didn't we do a guy today with proportions? And wasn't this P1 hat take away P2 hat over standard error? And wasn't the standard error some ridiculously ugly function? And that's why we tend to do it by calculator. Will you just trust me? I'm just telling you this is what the formula is. And yes, it is an equally ugly formula. It's the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Well, maybe not as ugly as before. And in fact, see if you do that one, isn't that just a standard error for a single sample? So it's not that different, right? So in this case, it's going to be the square root of 5 squared divided by 200 plus 3 squared divided by 250. And according to my calculator, let's see what that gets us. The square root of 5 squared, oops, wrong button, 5 squared divided by 200 plus 3 squared divided by 250. And I have a 0.401. Does this formula at least look like you could guess why it is what it is? Whereas the other P1 was weird, right? Now, this particular one was 130. This one is 127. And it's going to be divided by 0.401. So I'm going to get a Z-score. Let's see, I'm going to go 130, take away 127, and then divide that by 0.401. And I get a Z-score of 7.48. Do you think that's going to be statistically significant, that Z-score? Isn't the kind of rule of thumb bigger than 3, less than -3, you're probably going to come out fine. Right. But we continue the process. Let's get the p-value now. Well, it's going to be the probability that you get a Z-score, in this case greater than 7.48. Clear this out the way. Get our normal CDF guy. 7.48, 999 with a mean of 0 and a standard deviation of 1. And I'm getting one of those e to the -14 guys. Oh, time for conclusion. Is the p-value less than alpha? Well, is that guy less than 0.1? And the answer is yes. Where all these dotted lines go, I would be writing, this is a statistically significant result. Aren't male mountain lions heavier, right, than female mountain lions? Right? That's what the evidence is pointing towards, right? Statistically significant result that male lions are in fact heavier than female lions. Now I'm going to look at the raw data. 130 against 127. Yeah, they're different in weight. Do you think it's really that big a difference to be even bothered about? 3 pounds? Yeah, no. In fact, since males vary in weight and so do females vary in weight, won't there be a reasonable number of females that are heavier than the males? Right? Won't you get some males 125? Won't you get some females 127, 128? Right? So I would say statistically significant, but not that very interesting. Now, if this mean and that mean were, you know, like 40% heavier, I think that would be much more interesting, right? Wouldn't a zoologist say male mountain lions are significantly heavier than females? And they were using that word significant, not in the statistical sense, but more like in the it's big, right? Are we cool on that? So now we have to figure out how to get this p-value using all the data from my story. Now I'm going to hit start and I'm going to go to tests. And one of those guys in that page there, number 1 up to number 7, one of those guys is our guy. Sigma is known. I guess I should say sigmas are known. What do you do when there's 2 samples and you know?
Maybe number 3?
And the answer I just heard was that one. 2 sample Z.
So on the homework, it was a little confusing because they said like standard normal test. So I'm assuming that would be Z. But it was a little confusing because for a different one, when you're looking at data versus statistics, you do find them, you do find sigma, but I guess they were saying without taking that into account, it would be still using the Z or the T because we didn't know sigma. And I got that was a little confusing for me.
Right. If you know sigma, it's Z, and if you don't know sigma, it's T. And that'll get you out of all the weird ways in which they may phrase things to you, right? If you know the sigma, it's going to be Z, and if you don't know the sigma, it's going to be T. So let's kick this one in, and I'm going to use stats because in my data, that's exactly what I have. And sigma 1 was 5, and sigma 2 was 3, and X bar was 130, and the number of people in that sample was 200, and X bar 2 was 127, and the number of people in that sample was 250, and we were doing a greater than one, weren't we? So that would be our choice. And then I should just go down and hit calculate. And can you see that e to the minus 14 that we had? See that 3 point? I had 3.7, they had 3.8. Well, you just put that down to the fact that I rounded off quite badly. I mean, the calculator's going to do things to like 12 decimal places. So nobody's going to, I'm not going to ding you if you say 3.7 and it's 3.8, as long as the e to the minus 14 part, right? As long as it's got that bit, then I know you're in the right ballpark figure, right? So there is a bit of wiggle room. I suspect that when you do the homework, don't you tend to get a choice as 1, 2, 3, or 4, and the p-value is in one of those intervals, right? I think they're doing that because Marie, she's not very good. She doesn't like accuracy, so she does everything to 2 decimal places. But Rachel, she's a much better student, and she does everything to 8 decimal places. Can you imagine that your p-values are going to be different because of that? And they can't just put one number down, because Rachel could be right, but they picked Marie, right? And so I've came to a conclusion why that weird, instead of saying tell me the p-value, they just gave you a choice of intervals that it was in. And I think that kind of makes a little bit more sense now I've thought about it. And you know, by the way, Marie, I was picking on you because you are not that type of person. On the other hand, Rachel probably is very good at being accurate, so that might be true. No? Okay.
No, far from.
Well, if somebody gives you praise, just go with it. Right?
Okay, you say so.
Right? Definitely go for it. And there's enough negativity in the world. If somebody says something nice about you, I go for it. Yeah. True
I
story.
struggle with imposter syndrome, so that's why.
What's that? You believe you don't deserve to be here?
No, it's a thing where you just you discredit yourself because you think you're an imposter. That's my problem.
Oh, there must be. I have the opposite version of that. I think I'm much better than I really am. Is that just called arrogance?
Maybe.
Probably. But see, it's genetic. Scottish people are in general pretty arrogant. At least most of the ones I know are. Yeah. But then again, we've a lot to be arrogant about. Oh, come on, that was a good one. Yeah. I think because we're in week 6 that you're just not picking up my subtle humour anymore. So I'm going to have to tell you a really bad joke to get you back into thinking about it. I'm trying to think of some joke now because I need a break, just for a few minutes to give my brain a chance to absorb this. Hopefully for you to do it as well. So anybody got a theme, and I'll see if I've got a joke on it. Even better, tell me a joke, because that normally makes me think of another one.
Okay, I got one.
Go for it, Jenna.
Okay. How does a cow travel?
I don't know. How does a cow travel?
It moves.
Oh, we doing cow jokes. Okay. What do you call a cow with one leg? Lean beef. What do you call a cow with no legs? Ground beef. Okay, we're talking about maiming animals. Okay, then. What do you call... Oh, do you know Bambi from the movies? Right? You remember Bambi from the movies, the Disney movies? What do you call a blind Bambi? No idea. What do you call a blind Bambi that's had all her legs broken? Still no idea. Does it move still? No. Okay. Last one of that type then. Where would you find a dog with no legs? Don't know? Exactly where you left it. Oh, I get one hand clap out of all that hard work. Okay, I had to kind of beg for that applause there. Zoe, am I just going to get a smile off you? Is that the best I can do? Okay, I'll take what I get. You know, take whatever praise you get. I do have one last joke that I've got to get out of my head, which came in for no reason, and then we can go back to doing this fun stuff. And it's about Scottish people. there was a huge fire in an oil rig in Texas, right? The whole thing was, you know, the whole derrick had caught fire and the oil was shooting up and it was a big flame and it was really massive and quite extreme. And so the Texan starts getting on the phone call and he starts phoning up, you know, all the various specialized companies that put out oil rig fires. And every single company he tried was busy. There was evidently a lot of fire somewhere in Iraq and they were all being used. And so he phones up the last company and he talks about it and he says, look, I'm desperate. The guy says, we can't help you. The guy says, look, I'm desperate. I'll take any company. Is there any company out there that isn't busy? And the guy says, funny you should say that. I heard about this Scottish company. It's run by Scotsmen. It's Scots people who work for the guy. He says, I don't know if you should use them. They're not a very good company. From what I can tell, they've got virtually no money. They've got no equipment. They've just got people. You know, guy says, I'm desperate. So he gets the phone number and he phones up the Scottish guy and he said, told him about the oil rig fire. Guy says, not a problem. Me and my men will be there tomorrow. We'll put that fire out. Don't you worry. You know, the arrogance is kicking in. So next morning, just like the guy said, the Texan is there and it's at the bottom of the hill and right at the bottom of the hill is the oil rig and it's still blazing away. Flames coming everywhere. And he looks up at the top of the hill and he sees this beat up truck with flat tires, broken windows, lights don't work. And in the back, there's 6 guys and they've got shovels. And there's a guy in the truck driving and they come down the hill and he thinks, oh, they're going to stop and talk to me. But they don't. They just get faster and faster. And they zoom down the hill and they zoom by the Texan about 80 miles an hour. Right by him, don't even stop. Straight into the oil rig. Crashes into it, knocks the thing over. The guys in the back, first thing they're doing is putting out the flames with their hands on themselves, and then they're using their shovels and they beat and throw sand, and 30 seconds later, the oil rig is out, the fire's gone. The Texan's watching this and he's thinking, God, I've never seen that. And so the Scots guy comes back, he's still smouldering, right? He's still got smoke on him, and he comes back and he gets the check and he hands it over to him and says, Texan says, never seen a fire put out like that before. That was weird. That was unusual. But here's your money. You did the job. And he says to him, because it's a pretty good check, he says, what are you going to do with that money? The Scots guy says, you know, the first thing I'm going to do is get brakes for that bloody truck. Okay. Have you suffered enough? Shall we now continue with the classwork? Okay. So, well, where are we? Oh, yeah. We're on population means. Now, there's another version of that story, sigma unknown. Right? So imagine, I'll do 2 versions of this. When it's sigma unknown, don't even think about doing it the long way. I'm not even going to show you the long way. If you're really interested, just go and look at the textbook. 5 seconds into looking at it, you'll close the book and come back, right? You just want to know, right? I mean, that's doable, right? If you had time, this is doable, right? When sigma is known. When sigma is unknown, or you just get a list of data, which is essentially the same thing, right? If you get that, I would suggest strongly that you work on just using the calculator. So I need a story to do this too, so I'm trying to think of a story. Right. The average amount of time that it takes a male student to complete his test. Well, a big university where there are lots of students, they got a sample of 100 students, all taking the same test, and they timed how long it took them, because when they get the paper, they give the paper and they leave. And they found out that the average amount of time that these students took was 85 minutes. And then they had a group of female students, and there were 200 in this particular class, and the average amount of time that it took them was 86 minutes. And we want to know, is there evidence that, that the males take less time than the females? And we're going to do it on a significance level of 0.05. Well, I mean, superficially, would you agree that the males are 85 and the females are 86? So it does look like there might be evidence. See, even if I do get significant evidence, would you agree it's not that important? Yeah, a minute, who cares? It's not a biggie, right? But that doesn't mean that we can't prove it. Is your gut feeling this might be a no? It might not be statistically significant. Would you agree those numbers are really close? So it might not make it. So straight into the well, not straight into the calculator. Forgot the most important part. The null and alternate. The null and alternate don't care if sigma is known. Isn't the null always going to be that the two means are the same? It is. In this case, aren't we looking for a left-handed test? Okay, so what we're going to do now is get the calculator to do all the hard work. So it's going to do the heavy lifting. I'm going to hit start. I'm going to go over to tests. Sigma is unknown. Which of those guys is going to be our go-to guy?
T-test.
Are we getting comfortable with which one goes where for what reason? Right. Now, in this case here, it's a stat story. I think the next story I'm going to do is data, because I haven't shown you how to do data with these yet. So that's stats. In this case, it was 85. Oh, I forgot. You have to be told the standard deviation. So it would be in the question, right? So that would go there. The next one is 100. I apologize. I am getting a migraine. And what happens when I get migraines is, if you ever get them, you get the sparklies, the fireworks, and it goes for my central vision first, and then it goes out the way. So that's why I'm suffering to read, because I can't see it. I think X2 bar is 86, which is cool. And the standard deviation is 11. So if I screw up here, will you tell me I've got the wrong button? I think, would you agree that's the right data? Did I get it in right? Okay, so what I'm going to do now is I'm going to choose the less than, which I believe is that one, the middle one. And then we're going to go down. And here is an interesting question. Pooled, yes or no? In the story, they may tell you, we don't know the standard deviation, but we know that they're the same. For some reason, they know that they're the same. And if they say that, you will use yes. If in the story they don't mention it, or they say, we know for sure that they're not the same, but they probably won't say that, they'll just not mention it, then you will use no. So you always use no unless there is specifically instructed you in the story that although we don't know the standard deviations, we do know that they're the same. And that's what pooled is for, right? So pooled yes would be what you choose there. So I'm keeping it as no. And I've got calculate. And I am looking at lots of guys. Oh, shooting space. I'm pretty sure it's 0.14, but I'm having trouble. Is it? Well, I got a guy. 140.
Right.
140, good. Right. So, is our p-value less than alpha? Is 0.14 less than 0.05? The answer is no. So wouldn't we say this is not statistically significant? Now, I might as well share with you. I don't get migraines a lot. I used to anyway, not get them a lot. I tended to get them about once a month. I'm really lucky. I know a lot of poor souls get bad versions. I don't end up having to be in a dark room much. They normally go away in about half an hour to an hour. And I went to my doctor and he went and basically told me, and I'll do this when this is finished, that the reason you get migraines is, you know, at the back of your neck, there's some muscles there, and when they get tight and the blood flow restricts to your brain, that's typically what's causing a migraine. He said, drink Pepsi or drink some with caffeine and take a couple of ibuprofen, and it works really well. So if any of you have migraine, I've never been to a doctor. It's one of those treatments that won't kill you, right? Take some Pepsi and a couple of ibuprofen, and it works really well. But I am really lucky. I know lots of poor folk who are physically sick when they get migraines. I don't. I don't know why I'm getting them so much now. I think because I'm staring at a bloody TC screen for about 8 hours a day, 5 days a week virtually, because I have to do stuff when classes aren't going. And I think that is screwing up with my poor brain and my optic nerves. Is anybody else getting TV headaches because of this? Yeah, some of you are nodding. Yeah, what can you do? Okay, not statistically significant. I guess that's the end of the story, right? So one more example of this fella. Yeah, we got time. Let's suppose we have football players and we have basketball players. And this person believes that football players are on average heavier than basketball players. Now, I know basketball players are probably taller than football players on average, but aren't football players, a lot of them, not every position, but aren't a lot of them quite big, strong, strapping people, right? And aren't basketball players more lean and mean, right? Tall, but not a lot of weight. Right, so he's come to the same conclusion. So what he did is he found a random sample of 1, 2, 3, 4, 5, 6 of 7 football players, and then he got another random sample and make my life easy, of 5 basketball players. Now, in real statistical analysis, can you imagine that might be 200 and that might be 400, right? It would be decent sized numbers. So we're just doing this as showing how the process would work. But in reality, sample sizes of 7 and 5, wouldn't you really be, you should be really skeptical of any conclusions that you get, right? They're just not good data. But through circumstances, and so we can show you the process, we'll pretend that that's a okay thing to do. Now I'm going to hit stat, I'm going to hit test, and I'm going to hit I got it. Yeah. Now, where are we going this time? It's still a 2-sample t-test, right? Obviously, I don't know this fella. Oh, I should put in that alpha is 0.01, and that before I get too caught up on the data, won't we have that there's the same, and then won't we have that you're bigger, right? That's the conclusion. Okay,
Don't we need to go and put it into the list?
Oh, yes. Did you all catch that deliberate mistake? Okay. Yes, we do. Oh, this is going to be fun. 200, 250, 260, 280, 270, 280, and 270. If I kick over to the other side, 200, 210, 190, 230, and 260. Okay. Now I'll go back in. And we know we're doing the two sample t-test, right? Okay, so move over to data. And yeah, it's actually easier, isn't it, when it's data, because pretty much everything is there. And so, yeah, it's in L1. Isn't the other guy in L2? These are always 1. In this particular case, I want to prove the third option, right? I want to prove it's bigger. Can we just assume that it's no, because pretty much that's the most likely assumption anyway. And then we'll cancel down to calculate. And the p-value I got is 0.017. Now, when you do your homework, do you know very often they ask you to write down all this data? So if you need to write down X1 bar, can you see it's about 258? And if you want to write down X2 bar, do you see it's 218? And if they want to know, if I scroll down a bit, do you see you can get the standard deviations? I mean, the homework kind of asks you for all of that kind of stuff, right? So you don't need to calculate it. It'll be in this menu. Just scroll down for it. Let's look at this fella. Is our p-value going to be less than alpha? Is our p-value, which is this guy, going to be less than this fella? It's no. So this will be, it is not statistically significant. In other words, we haven't been able to prove this time that at a significance level of 1%, that football players are heavier than basketball players. Without changing anything else, suppose I had decided that I was going to use 5% significance level, right? Because I could. Would it have been statistically significant now? Would this be less than that? Yes. So how can the same set of data give contradictory answers? If you use a significance level of 1%, it's not statistically significant. But if you use a 5% level, it now does become statistically significant. Sounds like I'm lying here or cheating or something. I'm not.
Is it because you're using a wider interval, so like the confidence level is lower in the sense?
Right. So yeah, if you do a 5%, you're going to be wrong 5% of the time. If you do a 1% or 1%, can you imagine what the intervals look like? They shrink and they stretch accordingly. And so it is possible, isn't it, to be statistically significant at one of the significance levels, but not at the other. So in this case, it was a yes, but in this case, it was a no. And I'm sure I've mentioned that, but just in case I haven't, do you know that is one of the cheats that some unscrupulous people will do? They will get their data and they will analyze it and they will get their p-value. And once they see their p-value, then they kind of pretend that they were always going to use a 5% right at the start as well. So be on the lookout for, you can't really tell that if it's a one survey, right? But if they do lots of different combinations in one big paper, and you see that they keep moving the goalposts, it's significant at this level, significant at that level, I get a little bit suspicious. Because it sounds to me like they're cherry picking, right? They're deciding. And if you're doing it honestly, alpha should always be chosen at the start before you even look at the data. And that way that any statistical conclusions you come to are considered a bit more valid.
So if we're looking at it, it should have only one alpha and it should be a smaller alpha for significant, if it's valid.
If you want something that's statistically significant, isn't the smaller the alpha, the better? Because what the alpha does is it tells you how many times the conclusion that you've made is likely to be wrong. So if I do a hypothesis test at a significance level of 1%, do you know if I do 100 hypothesis tests, just like this one, 1 out of those 100 will actually be wrong even although I will say it's statistically significant, because it was. Because 1 in 100 times, in fact, couldn't I do 101 of these guys? Right, just find another 7 of these and find another 5 of these. Couldn't I do that 100 times? If I did it enough times, couldn't I eventually get a statistically significant result? You know, just by the variation of luck and chance. And that is a definite no-no. Can you imagine a scientist conducting an experiment and it didn't prove what he wanted? So he threw that data away and then he redid the experiment. And he just kept on doing it until one day he finally got what he wanted to see in the first place. And that's the one he publishes. Now, that will get caught out, because when you publish a scientific paper, apart from the peer review, which all their job is really to do is check, did you do it honestly mathematically? If you don't tell them, oh, this was the 83rd experiment before I got this, they're going to assume that you did it once and it worked out fine, and it will get by there. But the backup plan to that is whenever scientists see something, if you're working on the same field, oh, I'm going to try that just to see if I get the same results. And they will try it and they will not get the same results. And they will publish a contradictory paper. And then there'll be a little fight where I'm right, no, you're wrong, you're right, I'm wrong. And then somebody in Venezuela will be the arbiter and he'll say, I did it and you're wrong because I never got what you got, I got what he got, right? I got a not statistically significant result. And then you can imagine what happens to the reputation of that scientist. You know?
Is it okay to just do a hypothesis test twice? Like if the first time it doesn't work out?
See, now we're getting to the wobbly area, aren't we? I suggest strongly, if it doesn't work the first time, do it a second time, but do much bigger samples.
Yeah. Because
then at least you're trying to let the evidence do it and not the I'll keep throwing the coin until I get ahead, you know, technique, right?
Okay, yeah.
It's not uncommon, because experiments are very expensive, for there to be a small test with very small data sets that you have no intention of ever publishing, but you just want to see, does it look like it might be true? And if you think it might be true, then you give a little kind of paper to your dean and say, look, I'm working on neutrons and I think I've found something kind of interesting. You know, I've done a little experiment, you know, I spent a couple of days on it, and this is my kind of data. It looks like it might be true, but, you know, I can't prove it on this. Can you give me $100,000 and a big hydroscopic gizmo machine, whatever they use? And if you've got a really expensive, well-endowed university, they'll say, okay. And you get one, and then you do your big experiment, and then you publish a paper and you get a Nobel Prize or something, right? Or at least, I guess that would be the story. There have been lots of scientific experiments that have been done that cost a fortune and ended up being not significant. You never get to hear about them because nobody ever publishes non-significant results. But they happen all the time. There are a lot of pharmaceutical drugs out there that never hit the market. And they never hit the market because they did an evidence test like this to see if they were better. And they weren't, not statistically significant. So they didn't publish it. They didn't even make it, right? Which is one reason why drugs are so expensive. I don't know what the number is, but I think it's like 1 in 10 drugs actually make it to being manufactured and sold. So can you imagine a pharmaceutical company has to have 9 failures that cost a lot of money to get 1 success? So how do they make their money? They charge you a fortune the first time round. Yeah. I was just told by my doctor, I went to see him yesterday to cope with my many issues, and he was telling me that there is now a new testosterone treatment, which is a pill, instead of getting a liquid. And he told me it cost a fortune. So I said, I don't think I'm going to be using that. When it goes generic, it'll cost 10 cents. But before it goes generic, won't it be like $50 a pill? That's how they get their money. So maybe I do complain a lot about things like that. But if in my calmer moments, I cannot understand why. Right. In my calmer moments, which are not that often. Right, I think we get time for one last one. Right. So have you seen that basically you just type the data in and you come up with your conclusion? So since I am going to be doing one last question, I think what I'm going to do here, in case I forget, my migraine is going really well right now. I'm getting the fireworks now. That's the last stage. Anybody just share, anybody get migraines? Am I the only poor soul? Oh well.
I get migraines all the time.
You do, Kelsey? I call them fireworks. Do you get the firework thing?
Kind of like right behind the eye where it hurts really bad.
Okay. I mean, the different symptoms. I don't get much light sensitivity, which is good. I've heard of poor people that have to wear dark glasses and go into a dark room and like lie down for 2 hours. I'm not that person, thankfully. Are you like that? Yeah, okay. So, okay,
I used
let's.
to get them when I worked at UPS, but leaving a high stress job helps.
Oh, so are you telling me that I'm getting migraine because of you lot giving me stress?
Yeah, probably.
And I thought I liked you lot, but I don't know. If you're giving me migraines, I'm not so sure anymore. I don't think it's you lot. I might be stressed, that is true, but you're coming up on finals, and you know, my students coming up in finals stresses the heck out of me because I want you to be successful, and I keep worrying that maybe I haven't done something as well as I could have, or all that good stuff, and it kind of stresses me out too. So, okay, here we got, this is one question from the homework. Darn it in space, where are we? We got it. Are you looking at homework number 7? Right, okay, okay. I actually, I'm getting towards the tail end. The fireworks are dying down. Rapid eye movement sleep, I've heard of that, is sleep during which most dreams occur. Each night a person has REM and non-REM sleep. However, it is thought that children have more REM sleep than adults. Okay, that's interesting. Assume that REM sleep is normally distributed, and I'm just going through this data. Can you see this as data sigma is known? Right, so I'm just going to write down the key numbers here. So I'm going to have to figure out in the story who is 1 and who is 2. A random N1. Okay, 1 is kids, right, children, and 2 is going to be adults. Although you can't see this, you'll see it when I come back to it. And in the kids world, they did 9 children. Well, that wasn't a lot. And the average amount of hours where REM sleep was happening was 2.5, and that the standard deviation sigma 1 ended up being 0.7, right? And now I'm moving over to the adults, and they had only 9 of these adults, and the average amount of REM sleep that they had was 1.9 hours, and that sigma 2 was 0.5, and the significance level here is 1%. Okay, so I got all the data. Right, while we've still got this screen in front of us, let's do a couple of the questions, and then we'll go and we'll do the calculator, the analysis, right? In this case here, which one of these 4 guys would be the null and alternate hypothesis?
Is it the third one?
So the third one says they're the same, or that children are less than adult. New one is children, less than adults is that one. What does H2 say? They're the
It
same.
would be children
chil-
being more than adults, which is, I
Yes.
think that's what they're asking, right?
Yes. So children are more than adults. So in this case, it would be that one, right? Now, since sigma is known, this is their way of saying, which guy do you use? If sigma is known, don't you use Z's? And if sigma is unknown, you use T's. Remember that little mantra? If sigma is known, it's Z. If your sigma is unknown, it's T's. So the standard normal, we assume both distributions are approximately normal with known standard deviations. Now, the rest is going to come from your calculator, including that picture. So I'm now going to kick out of this and go in. Oh, it's cool when you can see. Right, just move in your. God, I've got a memory. I've been distracted. Did I take attendance? Let's just do that because I am going to zoom off and forget, and we don't want to not give you attendance. Okay, that's done. Oh, shooting space, I've lost you. Here we go. So that's basically the information that I sucked out of that story. Can you see it's all there? The kids, how many there were, how many of them, the average number of hours, and this guy. And over here, we've got the adults. So I'm going to hit stats, and we're going to move over here. And the first choice is, which one of those guys is the guy that we should be using based on the story that was given? We know sigma, so which one should it be?
Number 3.
Two sample, because it's two samples, right? Z, because we know sigma. And are we going to do data or are we going to do stats based on this information?
Stats.
So we hit it. And now we just basically type it in as asked. 0.7 and 0.5. And X1 bar was 2.5 hours. And the number in N1 was just 9. X2 bar was 1.9. And N2 was 9 again. And the null hypothesis is that there were the same amount of REM sleep. And the alternate is that mu1, the kids, was more than mu2, the adults. And so that would be this one at the end, agreed? And then I'll go down here and I'll hit calculate. And there's all sorts of numbers here. When they ask you for the test statistic, right, they're talking about the Z-score. So you just type in 2.09. And when they ask you for the p-value, that's a bit easier, right? It's this guy here. Right, so in my analysis here, the p-value is 0.018. So let's do the conclusion here. Shouldn't the test be, is the p-value less than alpha? Is 0.018 less than 0.01? Yes or no? No. Isn't that? It's not less than that. It's not. It's not less, it's not. Okay, that's boring. Right. not statistically significant. It would have been nice if it had been, because then I could say, that makes sense to me. I think when you're younger, you dream more, right? Isn't the world kind of fantasy land when you're a child? You're allowed to believe in dinosaurs and unicorns and cartoon characters and everything else.
But remember, it could potentially be, right? We just don't know.
It could be. We just don't know. I haven't proved that it's not true. Remember, not statistically significant doesn't prove that it's not, nothing's special. Kelsey, you have 2 dogs at the back now.
Yeah, they're a little rowdy right now.
Okay. It would be interesting if that was true. If it was true, wouldn't it probably get published in a newspaper article as well? But I think the mistake here, if you want to call it a mistake, I think it is, shouldn't you probably have a bigger sample size? I bet you if that sample size was larger, that I'd get a statistically significant result. So I'm going to pretend that it was. Can we pretend that it was 90 people, but you got the same answer, right? Shouldn't be too much to change our calculations. Basically, don't I just change that to 90 and change that to 90? And, oh, I forgot pooled. If sigma 1 was equal to sigma 2, because we know what it is, wouldn't I say yes? Pooled means the sigmas are the same. If you know what they are, it's easy to tell. Right, here's the calculation. And do you think this p-value is going to be a little bit smaller or a lot smaller?
A lot smaller.
Not when you're doing a mistake like I just did. So let me go in and fix it. So see what I did wrong. 7.5, okay. 2.5, 90, 1.9, 90. What's wrong with that? There's nothing wrong with that. But I got an error the first time, didn't I? I wonder if I hit the wrong button rather than the enter button. Okay, I would agree with you. Isn't that one of those e to the negative 11 things? If you could keep that data the same, right? If that's what happened, can you see what a a sample size of 90 can do to your analysis? Can't it make it much better? In reality, do you know if I did 90 of these, I would suspect that the numbers would probably come closer together. And because when there's 9 people, doesn't it only take 1 or 2 big ones to shift them one way or the other? When you do 90, that's going to get balanced by a couple of people who are hardly dream at all, and then you get something in the middle. But if that was the case, you see we've now got statistically significant, and we can say kids dream more than adults, which is cool. I believe dogs dream. I've told you this before, have I not? Yeah. Can I get at least one person to back me up here? Do dogs dream? Yeah. Kelsey, do your dogs dream?
Yes, they do.
Are you convinced, is it the way I'm convinced when they're sleeping, they do this little movement of their legs and they look like they're agitated and chasing something perhaps?
So that's what I always thought, but then I read something that was saying that that's not when they're dreaming. So I'm not really sure, but I'm almost positive that they do dream though.
Oh, I think they should, isn't it?
My dog has, well, my old dog, I think he used to growl in his sleep sometimes.
Okay, so whatever he was dreaming about was something he needed to growl about. Yeah. Right, our dogs, both of them do that. So I'm just going to go for the leg movement as them chasing something. Well, I think this is going to be our finish. We're at a good point today to stop.